In this next video, we'll begin with Chapter 1, Sample Exercise 4, and we're asked to find the density of mercury if we have 100 grams and that mass is occupying a volume of 7.36 cubic centimeters. So if you recall, the equation for density relates mass to volume in this fashion here. So if we were to plug in these values, we plug in 100.0 grams and then divide by 7.36 cubic centimeters. Um, we end up, after accounting for the correct amount of significant figures and then rounding, 13.6 grams per cubic centimeter. So this will be our answer to part A. Now we're asked in part B to calculate the volume of this liquid methanol if we're given 65.0 grams. And another name is wood alcohol for methanol. And we're given the density of 0.791 grams per milliliter. Remember, a milliliter is the same as a cubic centimeter. So we could report our answer in either volume if we needed to. So we're going to rearrange this equation that we used up here for just density to solve for volume now. So we're going to have, if we multiply both sides by V and divide it by D, we'll have volume is now equal to mass divided by density. So let's plug in the values that were given, 65.0 grams divided by 0.791 grams per milliliter. So we're going to solve for our volume in milliliters, and that comes out to be 3 sig figs because we have that many significant digits in each of our values, 82.2 milliliters. The last part here, part C, we're asked to solve for mass now. So we can once again rearrange that equation and say that mass is going to equal volume times density. And if we're given the density here of our gold, our cube of gold, and we're also given a length of the cube, we can solve first for volume. So volume is going to be length times width times height. So all three sides being the same in a cube, we would have 2.0 cubed, right? Right to the third power. So that will give us our volume of, we'll plug it in up here, 8.00 cubic centimeters, and then we will multiply by 19.32 grams per cubic centimeter. So we end up with a mass of 155 grams for this cube of gold. So we're going to continue here with our next section that is on the uncertainty in measurement. So I had mentioned the term significant figures in the last problem. We're going to expand on what that means in this section here. So when we talk about exact numbers, these are values that are known exactly. So another way of saying that is things that you can count. So you can count something and it is known exactly. When we talk about inexact numbers and how they differ from exact values, these are values that are measured. So these are measured values. And by measured, I mean using a ruler or a balance or a scale. And these measured values have some uncertainty associated with them. And depending on the precision of the instrument you use to measure something, we have different values for the uncertainty. So in this example here, we're asked to give it some thought to whether or not these values would be considered an inexact quantity. So the number of people here in part A in your chemistry class. So you can think, do you measure that with a balance or a scale, or do you count that value? So if you can count that on your fingers, that would be an exact number. Or maybe if you have a large class, maybe you have to use your toes. Then we have here in part B, the mass of a penny. So for that, you would have to use a balance or a scale. There would be some uncertainty depending on how precise your measurement was made, how expensive your instrument is. So that would be an inexact value. And then we have in part C here, the number of grams in a kilogram. This is an exact value. So we'll put an E here because this is a known quantity and there are specifically 1,000 grams in 1 kilogram. And that never changes. And this is actually considered what's called a conversion factor. So we can look at these two terms that I've mentioned. Well, I've mentioned precision, but I have not mentioned accuracy yet. Accuracy refers to how close you are to a known value. So close to known value, that's a way of determining how accurate you are. Precision refers to repeat measurements and how close those are to each other. So we'll say close to each measurement tells you how precise something is. Right? If your measurements are all very close together, you have precision in your data set. If they're not, then you can say that you lack precision. Um, so this term here that we'll define next, significant figures, this refers to the digits that were measured, how many digits were measured, and then the last digit would be approximated because that's the digit with the uncertainty. So when we round calculated values, so when we did our density calculation above, we have to pay attention to significant figures. So some of our figures might have 2 decimal places, some might have had 3. And then depending on what operation we're doing, whether it's addition and subtraction or multiplication and division, we would see different rules for how many significant figures to retain. And that is also we do not overstate our accuracy. Ooh, we kind of zoomed out there. So we don't want to overstate our accuracy of our answer. And so we'll talk about the rules of significant figures in the next video.